This is the second assignment of the tutorial 4. What we have to do is to find out the RMS value of a signal with a specific duration related to the average power level of the signal, and for that we have to write MATLAB program to compute that RMS value at each instant of the EMG signal. When you look at the EMG signal, we know the EMG signal has a actually lot of high frequencies. So, it does not give us a nice shape. So, how we can get that activity? One is that what is the frequency, another is that what is the amplitude of the signal. Here we are trying to find out the amplitude of the signal using that RMS value, and for that purpose we are provided with the signal that EMG doc2 dot dat, and we have to do the analysis of that local RMS for the different durations starting from 50 to 150 millisecond. Okay. We can take different windows 50, 100, so 150 in that way, and for each of these case we can see that how is that RMS local RMS estimates are varying, and here that RMS, that how to compute the RMS, that is also given, and what we are told that at least 2 different window duration we need to take, so that we can compare, and that window is giving us that how many samples should be there within that window, that is m. For that what we are doing, we are finding out the instantaneous energy, taking the average of the instantaneous energy, and while taking the average of the instantaneous energy, we take the half of it, rather we taking the square root of it. So, that the square root of the average of the instantaneous energy is gives us the RMS value. Okay. So, let us see that what we get out of this experiment. As with the previous cases, that we start with downloading the data and the MATLAB file to read them and keep them in that same directory, which is the working directory for our MATLAB. Okay. And with that we start our exercise. Here the first point is we have to read the EMG signal and we need to plot that. Okay. So, what we are doing? We are reading that signal, and that is taken as 10 kilohertz, and we are taking the length of it to find out the time index, and we are doing some normalization of it, and we are taking the plot of it. Okay. So, the job is to find out that envelope. Okay. Here is the EMG signal that is given, that we have plotted here, and next we go for the calculation of the RMS value. Okay. Calculation of the RMS value, that for that what we have done, we need to find out the m, that is the number of samples are there for different window length, and here we have chosen actually 4 window length. First is 50 millisecond, second is that 80 millisecond, third is 120 millisecond, fourth is 150 millisecond. Everything is expressed as that in terms of second, because the time axis is actually given in second, and here we have created a vector of m, and here the point is that out of that axis t, or rather vector t, it will find that what is the index of the t when it is becoming 50 millisecond. So, that value will come at the first place. Okay. Next one will give us the value when it is becoming same as the 80 millisecond. So, in other words, the first one will give us how many samples are there from starting point 0 to 50 millisecond. The next one will give us the number of samples up to 80 millisecond. The third one will give us the number of samples up to 120 millisecond, and fourth one will give us the number of samples with 150 millisecond. So, it is a compact representation, but we could do the same thing with more number of actually lines, though it would have been make actually it easy to understand. We could have gone that way also. Here just for the compact representation we have put it in that way. Next is that we are going through all the 4 different windows. So, we are taking a for loop going for 1 to 4, and each of these case we have to pad the EMG signal. So, for that padding, that a column signal, that here EMG P, the padded signal, is a row signal. So, we have taken the transpose, and both the sides we are taking that same number of actually zeros, okay, as that signal, that window size. Okay. So, we are padding it both the sides with that same number of zeros, so that we do not have any problem of actually the case that we are not getting the data. And if we look carefully, that here the number of that windows that is actually going to decide that what would be the amount of averaging on the RMS value. Okay. So, what degree of low pass filtering will be applied on the RMS. So, once we take that, then within that window we are computing the value R, that we are taking the sum of the energy divided by that window side and taking the square root of that. So, we get the RMS output. So, we get the RMS output. First we are showing the EMG, and below that in the subplot that 1 2 2 1 sorry 2 1 2 we are getting that RMS value for a particular window. Okay. First we start with the 50 millisecond, that is the first value here. So, we go for seeing that plot. So, here for 50 millisecond we get the output. We get that it is the way it is actually going up and down, it is following the same trend. However, it has lots of actually jagged points, okay. And in between, then when there are perturbations, that is also giving rise to some increase. Here we are getting that those things. So, they are also getting reflected as actually small peaks, okay, or like see it here that it is coming as a separate peak. So, all those things are there. Now, next is we go for 80 millisecond. With 80 millisecond, what we get, that the jaggedness of the output, it has reduced. If you look at here, that it is less jagged. Okay. If we go back, I think it would be easier to get that. Okay. That previous case 50 millisecond compared to that 80 millisecond, we have less of actually jaggedness. So, it has become much more smooth, and when we go for the 120 millisecond, it is even better. Okay. And another thing you note, that the small that perturbations all of them, their magnitude have also reduced a bit, they are also getting smoothed out. Okay. So, that is another interesting point to note, that it is becoming smooth and also the small perturbations they are getting eliminated. Now, we will go for 150 millisecond, and with that we get the 150 millisecond. This one is giving us the best output as it appears from the smoothness of the curve and that suppression of the small perturbations. Okay. Now, we go for that comparison of all of them together. Here we put all of them side by side, that first starting with the EMG signal, then 50 millisecond, 80 millisecond, 120 millisecond, 150 millisecond. As the window is small, it is actually fast in giving, actually responding to the small fluctuations. For example, that if we look at this fluctuation, it is visible here, but not so prominently here in 150 millisecond. Okay. So, the changes are slow, that is the downside when we are increasing the window length, but upside is here the envelope is much more smooth, that the envelope is much more smooth compared to that lower window size. Okay. So, that is the thing we observe here, and at the end we conclude it like this, that envelope of the RMS value obtained from bigger window size is smoother compared to the RMS value obtained from smaller window size, and envelope of RMS value obtained from bigger window size is slow to adapt to change in the signal. So, there is a trade off, we cannot keep on increasing the window size. If we do that, then the change in that signal envelope, it may not follow exactly, but so long it is not actually affecting that the tracking of that change of the envelope, we should keep on increasing the window size to get a smoother envelope. Thank you.